What if everything we see, touch, and experience is just the surface of reality, a tiny fraction of what truly exists? Picture standing in front of a vast, ancient tapestry, its threads woven into patterns so intricate they defy comprehension. From where you stand, you can only see a single thread, a sliver of the grand design, but pull back the fabric of the cosmos, and you might discover something astonishing: hidden dimensions folded into the very fabric of space and time, just beyond our perception. This isn't science fiction, it's one of the most thrilling frontiers of modern physics. For centuries, we've believed the universe operates in 3 dimensions of space and 1 of time. But what if there's more? What if the secrets of black holes, dark matter, and the very nature of existence itself lie in dimensions we can't yet see? The idea of hidden dimensions isn't just a wild speculation. It's a theory backed by some of the greatest scientific minds of our time. From Einstein's revelations about the warping of spacetime to string theory's proposal of 10 or even 11 dimensions, these concepts challenge everything we thought we knew about reality. Imagine a world where gravity leaks into other dimensions, where parallel universes brush against our own like shadows in the dark. These aren't just abstract ideas, they could hold the key to unlocking the deepest mysteries of the cosmos. Why does the universe behave the way it does? Why are the laws of physics so finely tuned? The answers might lie in realms we've only begun to theorize about, dimensions curled up so tightly they're invisible to us, yet shaping the very foundation of existence. This journey into the unseen isn't just for physicists, it's for anyone who's ever looked up at the night sky and wondered what's really out there. Over the next few minutes, we'll explore 30 of the most mind-bending theories about these hidden dimensions, from the cutting-edge mathematics of higher dimensional spaces to the eerie possibility that our entire universe is just one layer in an infinite cosmic stack. By the end, you might never see reality the same way again. So let's peel back the veil together and step into the unknown, because the universe is far stranger, far grander, and far more mysterious than we've ever dared to imagine. One of the most revolutionary ideas in modern physics is string theory's bold claim that our universe doesn't just operate in the familiar 3 dimensions of space and 1 of time. It's woven from at least 10, maybe even 11 dimensions. But if they're real, why can't we see or feel them? Think of a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line. But get close enough and you'll notice its surface curves around in a second dimension, forming a cylinder. Now imagine that hose is curled up so tightly, it's smaller than an atom. That's how string theory explains hidden dimensions. They're compactified, folded into microscopic shapes so tiny, our instruments can't detect them. These extra dimensions aren't just random folds, they're intricately sculpted into geometric forms called Calabi-Yau manifolds, complex 6-dimensional shapes that could dictate how particles and forces behave in our visible universe. Pioneers like Edward Witten, often called the father of string theory, have spent decades unraveling the mathematics behind these structures. The theory suggests that the vibrations of tiny, one-dimensional strings, not particles, are the fundamental building blocks of reality, and their dance through these higher dimensions determines everything from gravity to light. But here's the mind-bending part. If these dimensions exist, they could explain why gravity is so weak compared to other forces. While electromagnetism and nuclear forces are confined to our familiar 4-dimensional spacetime, gravity might be leaking into these hidden folds, diluting its strength in our observable world. It's like a sound wave traveling through a maze of rooms. What we perceive as a faint echo in our dimension might be a thunderous roar just beyond the veil. String theory isn't just about hidden geometry. It's a potential key to unifying quantum mechanics and general relativity, solving puzzles that have stumped physicists for over a century. Critics argue that without experimental proof, string theory remains a beautiful but unproven framework. Yet its mathematical elegance keeps drawing researchers deeper into the labyrinth of higher dimensions. Whether these realms are real or not, the mere possibility reshapes how we see reality, not as a static stage, but as a dynamic, multidimensional tapestry where every thread vibrates with hidden meaning. Now imagine our entire universe isn't floating freely in empty space. It's more like a single page in an infinite cosmic book. This is the Brane world scenario, where our three-dimensional reality is just one membrane or brane, existing alongside others in a vast higher dimensional space called the bulk. Think of it like a slice of bread in an enormous multidimensional loaf. We're stuck to our brain, unable to perceive the full scope of existence, while gravity and possibly other forces bleed into the bulk, stretching beyond the confines of our familiar dimensions. The roots of this idea trace back to M-theory, a bold extension of string theory that proposes 11 dimensions instead of 10. Physicists like Lisa Randall and Raman Sundram took this concept even further, suggesting that gravity's puzzling weakness could be explained if it weren't confined to our brain at all. Picture a flashlight shining through layers of fabric. Most of its light gets trapped between the threads, but some escapes into the darkness beyond. Similarly, gravity might be the only force leaking into the bulk, diluting its strength in our world while remaining strong in others. This isn't just about gravity, though. The Brane world scenario might also solve the hierarchy problem, one of physics' biggest head-scratchers, which asks why gravity is so astronomically weaker than other fundamental forces. If particles like electrons and quarks are anchored to our brain, their influence stays concentrated here, while gravity's reach extends into the bulk, spreading thin like ink diffusing through water. Randall and Sundram's models suggest that warped geometry in the bulk could amplify this effect, creating the stark imbalance we observe today. But here's where it gets wilder. If other branes exist parallel to ours, they might harbor entirely separate universes with different physical laws, cosmic neighbors forever hidden from view. Collisions between branes could even explain cataclysmic events like the Big Bang, as if our universe was born from a ripple in the bulk. While we've yet to detect direct evidence of these shadow dimensions, experiments at the Large Hadron Collider continue hunting for clues, like miniature black holes that might wink in and out of existence if gravity truly slips between branes. The Brane world scenario isn't just a theoretical playground, it challenges us to rethink the very nature of reality. Are we alone on our membrane, or is the bulk teeming with unseen worlds? If higher dimensions exist, they might not just be hidden, they could be everywhere, pressing in on us, shaping the fabric of our existence in ways we're only beginning to glimpse. What if everything we perceive as depth, texture, and dimension is nothing more than an illusion, a cosmic trick of the light? This is the startling premise of the holographic principle, a theory suggesting our three-dimensional universe might actually be encoded on a distant two-dimensional surface, like a movie projected from the edges of reality. The roots of this idea trace back to an unexpected source, black holes. When scientists like Leonard Susskind studied these cosmic enigmas, they stumbled upon a paradox. Black holes seem to destroy information as they evaporate, violating quantum mechanics' core rule that information can never be lost. But what if that information isn't truly gone? What if it's preserved pixel by pixel on the black hole's event horizon, the point of no return? Think of it like a fingerprint pressed into glass. From one angle, it appears flat and lifeless. But tilt the glass just right, and the ridges spring into three-dimensional relief. The holographic principle argues our universe works the same way. All the stars, galaxies, and even your consciousness could be shadows cast by data etched onto a vast, unseen canvas. This isn't poetic metaphor. It's grounded in the AD/CFT correspondence, a mathematical framework showing how a higher dimensional space like ours can perfectly mirror the physics of a lower dimensional boundary. Imagine a snow globe containing an entire winter village. The holographic principle suggests the real magic isn't inside the globe. It's painted on its curved glass walls, with every snowflake and lamppost encoded in intricate detail. Suskind's breakthrough revealed something even stranger. The information needed to describe any volume of space doesn't scale with its size. It's limited by the area of its surface. It's as if the universe has a built-in resolution limit, like a digital screen where adding more pixels doesn't increase clarity beyond a certain point. This flips our intuition about reality upside down. We're used to thinking the world becomes richer the deeper we explore, but the holographic principle hints the opposite may be true, that the ultimate truth lies not in the depths but on the edges. Critics argue the theory remains speculative, lacking direct experimental proof, yet its implications ripple across physics, offering fresh ways to tackle quantum gravity and the nature of spacetime itself. If the holographic principle holds, it would mean the universe isn't just stranger than we imagine, it's stranger than we can imagine, a shimmering mirage spun from pure information. Every galaxy, every atom, every fleeting thought might simply be lines of code written on the fabric of reality's farthest shore. Long before string theory proposed its 10-dimensional universe, a quiet revolution was brewing in the shadows of physics. In 1919, mathematician Theodore Kaluza made a startling observation. If Einstein's equations for gravity were rewritten in 5 dimensions instead of 4, an extra term appeared, one that perfectly described Maxwell's equations for electromagnetism. It was as if the universe had been whispering its secrets in a hidden language all along. Kaluza's colleague Oscar Klein later refined the idea, suggesting this 5th dimension wasn't some vast, unexplored frontier. It was curled up into a loop smaller than an atom, a cosmic thread too tiny for any microscope to see. Picture an ant crawling along a telephone wire. From a distance, the wire seems like a simple one-dimensional line, but to the ant, the wire's circular cross-section reveals an entirely new dimension of movement. Kaluza and Klein proposed our universe might work the same way, with gravity and electromagnetism unified in a higher dimensional space, but with the extra dimension compactified, rolled up so tightly it disappears from everyday view. The scale of this hidden dimension is almost incomprehensibly small, on the order of the Planck length, about 1/trillionth of a trillionth the size of a proton. At that scale, even the most powerful particle accelerators can't detect its presence. This elegant unification came with a tantalizing implication. The properties of particles might not be fundamental at all, but rather artifacts of how they move through these compactified dimensions. An electron's charge, for instance, could emerge from its momentum as it spirals around the unseen 5th dimension, like a planet's orbit, creating the illusion of seasons. Though the theory couldn't explain the newly discovered nuclear forces, it planted a seed showing that hidden dimensions might solve problems that seemed insurmountable in classical physics. Modern string theory owes much to Kaluza-Klein's legacy. Their compactification idea became a blueprint for how extra dimensions could exist without contradicting our 4-dimensional experience. But where Kaluza and Klein saw a single curled-up dimension, string theorists now envision 6 or 7, folded into intricate Calabi-Yau shapes. The mathematics grew more complex, but the core insight remained. The universe might be far richer than it appears, with every force and particle dancing to the tune of hidden geometries. Critics point out that Kaluza-Klein theory couldn't predict new phenomena or explain quantum quirks, leading many to abandon it by the mid-20th century. Yet its spirit lives on. The notion that dimensions beyond our perception could unify nature's forces continues to drive theories like supersymmetry and Brane worlds. Even if the 5th dimension remains forever elusive, Kaluza and Klein's work reminds us that sometimes the key to understanding reality isn't looking deeper, but realizing we've been missing an entire direction. What if every particle in the universe has a hidden twin, a mirror image lurking just beyond our perception? This is the radical promise of supersymmetry, a theory suggesting that the fundamental building blocks of reality come in pairs, connected through the hidden symmetries of extra dimensions. At first glance, the idea seems simple. For every known particle, like an electron or quark, there should exist a heavier, undiscovered counterpart with flipped quantum properties. Electrons would have selectrons, photons would have photinos, and the entire cosmic menagerie would double in size overnight. But beneath this elegant symmetry lies a profound truth. These superpartner particles could be vibrating through dimensions we can't see, weaving together forces and matter in ways that rewrite the rules of reality. Supersymmetry, often called SUSY by physicists, emerged as a solution to some of quantum mechanics' most nagging inconsistencies. The standard model of particle physics treats fermions particles like electrons that make up matter, and bosons particles like photons that carry forces as fundamentally separate. SUSY shatters this division, proposing they're two sides of the same coin, linked through higher dimensional symmetries. Picture a dance where every spin has a counterspin, every step a mirrored counterpart. In this cosmic ballet, fermions and bosons aren't just partners, they transform into one another through dimensions we've yet to map, revealing a deeper unity beneath the apparent chaos of quantum behavior. The implications ripple far beyond neat mathematics. If superpartners exist, they could solve one of cosmology's greatest mysteries, dark matter. The lightest superpartner, often dubbed the neutralino, wouldn't interact with light or ordinary matter, making it invisible to telescopes yet heavy enough to account for the gravitational glue holding galaxies together. It's as if the universe has been leaving us breadcrumbs in the form of missing gravity, and SUSY offers the first real trail to follow. Experiments at the Large Hadron Collider have spent years hunting for these elusive particles, smashing protons together at nearly the speed of light, hoping to catch a fleeting glimpse of a selectron or squark emerging from the debris. So far, the detectors remain silent, but the search has only narrowed the possibilities, not ruled them out. Critics argue that SUSY failure to appear in experiments threatens its credibility, while supporters counter that we might simply be looking in the wrong energy range, or that superpartners could be hiding in curled-up dimensions beyond our current reach. The theory remains compelling because it doesn't just tidy up particle physics. It suggests that the forces we perceive as separate electromagnetism, the strong and weak nuclear forces, even gravity, might unify in higher dimensional space, merging into a single, elegant framework. Imagine a scattered puzzle where each piece seems unrelated until you step back and see the full, multidimensional picture. Beyond the math, SUSY hints at something poetic, that reality, for all its apparent complexity, might be built on harmonies we're only beginning to hear. Whether superpartners are discovered tomorrow or remain forever beyond our grasp, the theory challenges us to think bigger, to consider that every particle we know might be half of a story written in the hidden folds of the cosmos. And if that story turns out to be true, it wouldn't just change physics, it would redefine our place in a universe far more interconnected than we ever dreamed. Imagine waking up one morning to discover your entire world is just a tiny soap bubble floating in an endless cosmic sea, one among countless others, each with its own unique laws of physics. This isn't the plot of a sci-fi novel, it's the startling vision of eternal inflation, a theory that reshapes our understanding of reality itself. The story begins in the late 20th century, when physicist Alan Guth proposed a radical solution to some of the universe's biggest puzzles. Why is the cosmos so uniform on large scales? Why does space appear flat rather than curved? Guth's answer was inflation, a moment of exponential expansion in the universe's first fraction of a second, stretching quantum fluctuations into the seeds of galaxies. But the implications didn't stop there. If inflation could happen once, what's to stop it from happening again and again, forever? Eternal inflation takes this idea to its dizzying extreme. Picture an infinite, seething higher dimensional space where quantum fluctuations constantly spawn new, bubble universes. each inflating into its own isolated cosmos with its own rules. In this view, our universe isn't special. It's just one accidental pocket where the conditions happen to allow stars, planets, and life. Other bubbles might have stronger gravity, slower light, or even extra spatial dimensions unfurled to macroscopic sizes. Some could be barren, collapsing instantly. Others might shimmer with bizarre forms of matter we can't begin to imagine. The terrifying beauty of this model is that it doesn't require fine-tuning. Instead of asking why our universe seems perfectly calibrated for existence, eternal inflation suggests an answer. We're simply in one of the rare bubbles where the dice rolled in our favor. The math behind this theory hinges on the properties of the inflationary field, a kind of energy that drove the universe's initial expansion. Like water freezing into ice, this field can decay from a high-energy state to a lower one, releasing energy that forms a new bubble universe. But here's the twist. In regions where decay hasn't occurred, inflation continues indefinitely, creating a self-replicating fractal of cosmic bubbles. It's like a pot of boiling water where every rising vapor bubble spawns more bubbles within it, ad infinitum. The resulting multiverse isn't just vast, it's ceaselessly generative with no beginning or end, only an endless branching of possibilities. Critics argue that without observable evidence, eternal inflation remains speculative, a dazzling mathematical construct without empirical grounding. Yet its explanatory power is undeniable. It accounts for the eerie uniformity of the cosmic microwave background, while also explaining the universe's bafflingly low entropy at the Big Bang. Even more provocatively, it offers a potential link to string theory's landscape of possible vacuums, suggesting that each bubble universe might choose a different configuration of hidden dimensions and physical constants from an almost infinite menu. The philosophical implications are staggering. If eternal inflation is true, then every conceivable universe exists somewhere in the multiverse, from worlds nearly identical to ours to realms where time flows backward or gravity repels. This doesn't just challenge our place in the cosmos, it redefines reality as a cosmic game of chance, where we're both spectators and unlikely winners. While we may never peer beyond our bubble's boundaries, the theory invites us to consider a universe far grander and more mysterious than we ever imagined. One where the Big Bang wasn't the beginning, but just a single note in an endless symphony of creation. What if the Big Bang wasn't the beginning of everything, just the latest chapter in an endless cosmic cycle? This is the audacious claim of cyclic cosmology, a theory that rewrites the origin story of the universe by turning to the hidden geography of extra dimensions. At the heart of this idea is physicist Paul Steinhardt's vision of colliding branes, those multidimensional membranes we encountered earlier crashing together like titanic symbols in the void, triggering not one but countless rebirths of spacetime. Forget a single explosive beginning. Steinhardt's model proposes a universe without start or end, where expansion and contraction play out in an eternal loop. The mechanics hinge on the dance of these branes through higher dimensional space. Picture two sheets of paper floating parallel to each other in a dark room. Now imagine them slowly drawn together by an unseen force, warping as they approach. When they finally collide, the impact releases enough energy to recreate an entire universe's worth of matter and radiation, a new Big Bang. But instead of emerging from a singular point of infinite density, this reboot springs from the violent yet structured meeting of branes in the bulk. The process isn't chaotic, it's governed by the intricate geometry of extra dimensions, with each collision resetting the cosmic clock while preserving subtle traces of previous cycles. This solves one of the thorniest problems in cosmology, the singularity. Traditional Big Bang theory hits a wall when rewinding time to t=0, where equations break down in a storm of infinite heat and density. Cyclic cosmology sidesteps this entirely. the branes never collapse to a point; they rebound, carrying information from cycle to cycle like a cosmic baton. Even the arrow of time might flip during each transition, meaning entropy doesn't accumulate across cycles but resets, avoiding the heat death that plagues other models. Supporters argue this framework elegantly explains cosmic quirks like the uniformity of the microwave background. In standard inflation, patches of space too distant to have ever interacted somehow share identical temperatures, a puzzle requiring ad hoc solutions. But in cyclic cosmology, these regions could have been in contact during a previous cycle, their properties imprinted long before our current universe's birth. The theory also predicts gravitational wave patterns distinct from inflation, offering testable differences. Yet challenges remain. Critics note the model requires exquisitely fine-tuned initial conditions to ensure branes align perfectly for cyclical collisions. Others question whether quantum effects at impact would truly preserve information across eons. But Steinhardt's vision endures because it reimagines time itself, not as a line with one beginning, but as a Möbius strip of creation, where every ending births a new beginning in the hidden depths of the bulk. The implications are profound. If cyclic cosmology holds, our universe isn't a one-time fluke but one note in an infinite symphony, with each crescendo of colliding branes composing fresh verses in the song of existence. And somewhere in those higher dimensions, the next movement may already be tuning up. The smooth, continuous fabric of spacetime we take for granted might be nothing more than an illusion, a cosmic mirage hiding reality's true pixelated nature. At the heart of loop quantum gravity, a bold alternative to string theory, lies a radical idea. Spacetime isn't an infinite canvas but a shimmering mosaic of unimaginably tiny grains, each no larger than the Planck length, about 1/1,000,000,000 of a trillionth the size of a proton. Imagine zooming in on a digital photograph until you see the individual pixels. Loop quantum gravity suggests the universe works the same way, with every passing second and every stretch of space built from discrete, indivisible quanta. These aren't just mathematical abstractions, they're the building blocks of reality itself, woven into a dynamic network of intersecting loops that give the theory its name. Unlike string theory's reliance on hidden extra dimensions, loop quantum gravity stays firmly grounded in our familiar form, focusing instead on reimagining spacetime's very structure. Picture a bustling city seen from space, a glow of continuous light, but descend closer and you'd spot individual streetlights, cars, and windows. Loop quantum gravity argues spacetime behaves similarly, appearing smooth from afar but revealing its granularity when probed at the Planck scale. These spacetime atoms aren't static, they vibrate, merge, and split, creating the evolving geometry we experience as gravity. The theory's pioneers like Lee Smolin and Carlo Rovelli describe it as a cosmic spin network where each link represents a quantum of space and each node a moment of time, stitching together the universe one interaction at a time. The contrast with string theory is striking. While string theory seeks harmony by adding dimensions, loop quantum gravity finds complexity by diving deeper into the ones we know. String theorists envision hidden dimensions curled into intricate Calabi-Yau shapes, governing particle behavior from afar. Loop quantum gravity, meanwhile, suggests that even within our 4 dimensions, spacetime's granularity could generate emergent phenomena, like how the collective motion of water molecules gives rise to waves. This granular structure might leave fingerprints in high-energy cosmic rays or subtly alter the speed of light across different wavelengths, offering potential paths to experimental verification. Yet both theories share a common goal, reconciling Einstein's general relativity with quantum mechanics. Where string theory smooths over their contradictions with extra dimensions, loop quantum gravity tackles them head-on by quantizing spacetime itself. It's the difference between adding rooms to a house to resolve a cramped space versus rebuilding its foundation brick by brick. The theory's mathematical elegance lies in its simplicity. no unseen dimensions, no unobservable strings, just space-time broken down to its most fundamental pixels. Critics argue that without experimental evidence, loop quantum gravity remains speculative, its predictions hovering at energy scales far beyond current technology. But its implications are profound. If space-time is granular, then concepts like before the Big Bang take on new meaning. The theory suggests our universe might have emerged from the quantum bounce of a previous cosmos's collapse, avoiding the singularity problem entirely. Black holes, too, could reveal their secrets differently. Their cores might not be infinitely dense points, but dense knots of space-time quanta, rewriting our understanding of event horizons. Whether spacetime's hidden structure unfolds in extra dimensions or in the dance of quantum loops, one truth remains: reality is far stranger than it seems. The challenge isn't just to uncover these layers, it's to reshape our intuition, to see the universe not as a stage but as a living, evolving fabric, stitched together by forces we're only beginning to glimpse. Dark matter has been the universe's most stubborn riddle, an invisible substance that refuses to interact with light, yet outweighs ordinary matter 5-1. But what if its elusiveness isn't just a property of the particles themselves, but a clue to something far stranger? Imagine a world where certain particles don't just pass through walls, they slip between the very dimensions of space, flickering in and out of our perception like shadows cast by a flickering candle. This is the radical suggestion that dark matter might not be missing at all, it could be hiding in plain sight, woven into the fabric of higher dimensions. The idea builds on a subtle twist in how particles interact across dimensions. In our familiar three-dimensional world, forces like electromagnetism bind atoms together with obvious strength. But gravity behaves differently, comparatively feeble, as if diluted by unseen factors. Some theorists argue this isn't a coincidence. If dark matter particles, unlike ordinary matter, are free to move through extraspatial dimensions, their gravitational influence would still reach us, while other interactions, like those with light, would be muted or redirected into dimensions we can't access. Picture a crowd of people shouting in a vast auditorium. You'd hear those standing near you clearly, but voices from a balcony high above might reach your ears as faint whispers, their origins unclear. Dark matter could be calling to us from those hidden balconies of reality. One compelling model for this comes from the universal extra dimensions framework, which suggests that while photons and electrons are confined to our three-dimensional brain, dark matter particles might be bulk matter, free to traverse the full geometry of higher dimensional space. These particles wouldn't just occasionally dip into our world, they'd exist primarily outside it, with only gravity tethering them to our observable universe. When galaxies spin faster than visible matter can explain, it's not because of some exotic particle, it's because we're feeling the gravitational echo of matter, whose true mass is distributed across dimensions we can't see. Experiments haven't yet ruled out this possibility. In fact, certain anomalies in cosmic structure align eerily well with predictions of higher dimensional dark matter. For instance, some dwarf galaxies exhibit dark matter distributions that appear smoother than standard models predict, as if the missing mass isn't clumping in 3 dimensions but is instead smeared across unseen directions. Even more intriguingly, if dark matter interacts through extra dimensions, it could explain why detectors like Xenon and LUX, designed to catch rare collisions with ordinary matter, keep coming up empty. The particles aren't just shy, they might be fundamentally out of reach, like fish swimming beneath the surface of a pond we can only skim. Critics rightly point out the challenge of testing dimensions we can't observe. Yet the theory offers tantalizing solutions to multiple puzzles at once. It accounts for dark matter's gravitational grip while explaining its invisibility, and it sidesteps the need for undiscovered particles in the standard model's zoo. Even the perplexing absence of dark matter in certain galaxies could make sense if those regions happen to sit where extra dimensions pinch off, weakening the particle's influence. The universe might not be missing matter at all. It could be that we've been searching for shadows while ignoring the higher dimensional objects casting them. Perhaps the most poetic implication is this: if dark matter truly resides in extra dimensions, then every galaxy, including our own, is haloed by an invisible architecture, a hidden lattice of mass and gravity stretching into realms beyond our perception. What we call the cosmic web of dark matter might just be the three-dimensional imprint of something far grander, a multidimensional tapestry we're only beginning to trace in the faintest of outlines. And if we ever learn to detect these dimensional whispers directly, it wouldn't just solve a mystery, it would throw open a door to realities we've never dared to imagine. We often think of time as an unstoppable river, flowing in one direction at a fixed pace, but what if that's just an illusion? What if time isn't a current carrying us forward, but a dimension we could navigate, like climbing a mountain or turning a corner? This radical idea isn't science fiction. It's woven into the very fabric of Einstein's general relativity, where time and space fuse into a single flexible entity called spacetime. And in this four-dimensional tapestry, time might be far more malleable than we ever imagined. Take Kurt Gödel's rotating universe, a solution to Einstein's equation so bizarre it suggests the entire cosmos could spin like a vast whirlpool, dragging time itself into loops where past and future blur. In such a universe, you could set off on a journey through space and return before you left, meeting your younger self in a paradox that defies common sense. Gödel's model wasn't just a mathematical curiosity, it exposed a profound truth about reality's structure. If the universe rotates globally, it generates closed time-like curves, paths through spacetime that circle back on themselves like a Möbius strip. These aren't mere hypotheticals, they're consequences of relativity's core principle. Mass and energy bend spacetime, and in extreme cases, that bending could twist time into a knot. Picture a record spinning on a turntable. Near the center, the grooves are tight and orderly, but toward the edge, the spiral stretches, and if the record spun fast enough, those outer grooves could cross over themselves, creating loops where the needle retraces its path. Gödel showed that spacetime, under the right conditions, could do the same. This challenges everything we assume about causality, the bedrock of science that insists causes must precede effects. If time loops exist, then events could become self-creating with no clear origin. A photon might arrive at a detector before it's emitted from its source, or a traveler could become their own ancestor. Einstein himself was troubled by these implications, calling them disturbing yet unavoidable within the math. Modern physicists like Kip Thorne have explored similar terrain, showing how wormholes, bridges through spacetime, could function as time machines if stabilized by exotic matter. The key lies in general relativity's flexibility. Time isn't an absolute backdrop but a dynamic player, warping and stretching under the influence of gravity and motion. Yet for all its theoretical elegance, Gödel's universe clashes with observation. We see no evidence of a rotating cosmos. Galaxies drift apart in all directions without any global spin. But the deeper insight remains valid. Time's flow isn't intrinsic, it's contextual, shaped by the universe's geometry. Near a black hole's event horizon, clocks tick slower as seen from afar. At light speed, time would stop entirely for the traveler. These aren't quirks but features of time's dimensional nature, as real as the up-down axis of space. Even our everyday sense of now might be an artifact of perspective, like mistaking a single slice of bread for the whole loaf. The paradoxes that arise, grandfather paradoxes, bootstrap paradoxes, aren't flaws in the theory but invitations to think differently. If time is a dimension, then before and after might be as relative as left and right. Some physicists like Sean Carroll argue that these loops don't violate causality but redefine it, with physics self-correcting to prevent inconsistencies. Others propose branching timelines or parallel worlds to resolve the contradictions. one thing is certain: if time is truly a traversable dimension, then the universe is stranger than we dreamed, a labyrinth where the walls themselves are woven from the threads of past, present, and future, waiting to be unraveled. The Big Bang wasn't a beginning, it was a cosmic car crash. That's the explosive premise of the ekpyrotic universe, a theory that rewrites creation's origin story, not with a singularity, but with a collision between worlds in the hidden depths of higher dimensional space. Picture two enormous parallel sheets of reality branes floating in a fifth dimension, separated by a gap narrower than an atom. These aren't static membranes, they're dynamic universes unto themselves, warping and rippling under quantum fluctuations until boom. A shattering impact that doesn't destroy but creates. The energy of that collision wouldn't just produce heat and light, it would birth entire galaxies, stretching and cooling into the cosmos we recognize today. The theory's architects, Justin Cowrie, Bert Overath, and Paul Steinhardt, took inspiration from string theory's brane worlds but flipped the script on inflation. Instead of a universe ballooning from nothingness, the ekpyrotic model offers a dramatic reset, cyclical collisions between branes, each crash triggering a new cosmic era. It's as if our universe is stuck in an endless hall of mirrors, where every reflection is a fresh Big Bang, each one leaving faint echoes in the next. This solves one of inflation's biggest headaches, the singularity problem. When cosmologists rewind time to the Big Bang, equations spit out infinities where density and temperature become meaningless. But in the ekpyrotic scenario, there's no singularity, just a transfer of energy between branes at a finite, if unimaginably high, temperature. Gravity plays a surprising role here. While other forces like electromagnetism stay confined to our brane, gravity's reach extends into the bulk, the higher dimensional space between membranes. As the branes draw near, gravitational attraction warps their surfaces, creating fluctuations that later seed galaxies. This subtle dance avoids the fine-tuning required by inflation, where initial conditions must be exquisitely calibrated to match observations. Instead, the ekpyrotic model generates density variations naturally, like wrinkles forming on a cloth pulled taut. Critics highlight tough questions: what keeps branes aligned for perfect collisions across eons? Why hasn't the Large Hadron Collider detected signs of extra dimensions? Yet the theory's elegance keeps it alive. It doesn't just sidestep the singularity, it offers testable differences. Inflation predicts a smooth, Gaussian distribution of cosmic microwaves, while ekpyrosis suggests sharper, non-Gaussian patterns. Future telescopes hunting these fingerprints could tip the scales. The philosophical implications are staggering. If correct, our universe isn't a one-time miracle but a phase in an eternal cycle, each collision wiping the slate clean while preserving traces of the past. Time becomes a spiral, not a line, a series of fresh starts echoing in the dark between dimensions. And somewhere out there, another brane may already be drifting toward us, carrying the next iteration of reality in its wake. Einstein famously called it spooky action at a distance, the bizarre phenomenon where two entangled particles instantaneously influence each other, no matter how far apart they are. Quantum mechanics treats this as fundamental, but what if the spookiness isn't inherent to the particles? What if their connection isn't magical but geometric, woven through dimensions we can't see? This startling possibility reimagines entanglement not as a mysterious force, but as particles literally touching through higher dimensional space, like fingertips brushing against each other from opposite sides of a folded piece of paper. Imagine two ants crawling on a sheet of paper separated by an impassable crease. From their two-dimensional perspective, they're isolated with no way to reach each other. But fold the paper just right, and suddenly their paths cross their neighbors in three-dimensional space, even while appearing distant on the flat surface. This is the core idea behind higher dimensional entanglement. particles that seem impossibly linked across vast stretches of our three-dimensional universe might actually be inches apart when measured through an unseen fourth spatial dimension. Their action isn't happening at a distance, it's happening locally in a geometry we're blind to. The math supporting this isn't just speculative. Models like the AD-S/CFT correspondence, a framework linking higher dimensional gravity to quantum field theories, suggest that entanglement entropy in our three-dimensional world could mirror the geometry of wormholes or extra dimensions. In simpler terms, what looks like quantum weirdness here might be the shadow of perfectly ordinary interactions occurring in a larger spatial arena. Even string theory hints at this. When open strings vibrate through extra dimensions, their endpoints on our brain could manifest as entangled particles, forever bound by threads too tiny to detect. What makes this geometric view so compelling is how neatly it sidesteps the usual paradoxes of non-locality. Instead of violating relativity's cosmic speed limit, entangled particles might simply be bypassing our three-dimensional roadblocks entirely, communicating through shortcuts in the bulk of higher dimensional space. It's the difference between shouting across a canyon and whispering through a hidden tunnel. The message arrives instantly, not because it broke the rules, but because it followed a path we hadn't considered. Experiments haven't yet confirmed these extra-dimensional links, but the theory offers tantalizing predictions. If entanglement relies on hidden geometry, then manipulating spacetime curvature near a black hole or in advanced lab settings might alter quantum correlations in measurable ways. Some researchers even propose that the famous double-slit experiment could reveal dimensional fingerprints. Particles interfering with themselves might actually be tracing paths through warped higher dimensional terrain. Of course, skeptics argue that invoking unseen dimensions risks explaining one mystery with another. Yet the elegance of this approach lies in its economy. It doesn't invent new physics, but reinterprets existing phenomena through a broader spatial lens. Whether entanglement secrets are locked in extra dimensions or not, the very possibility reshapes our understanding of connection, suggesting that the universe's deepest bonds might be written in directions we've yet to perceive. And if that's true, then every quantum link, every spooky action, could be a fleeting glimpse into the hidden architecture of reality itself. String theory doesn't just hint at hidden dimensions, it paints a cosmos of staggering diversity, where the fabric of reality could exist in 10 to the 500th power possible configurations. That's a 1 followed by 500 zeros, a number so vast it dwarfs the atoms in the observable universe. Each of these configurations, or vacuum states, represents a unique universe with its own dimensionality, physical constants, and laws, some with 6 curled-up dimensions, others with 7, some where gravity is stronger than electromagnetism or where time flows in loops. This unfathomable tapestry is known as the string theory landscape, and it redefines not just what the universe is, but what it could be. At the heart of this idea lies a simple but profound question. Why does our universe have exactly 3 spatial dimensions, a weak gravitational force, and a cosmological constant fine-tuned to allow stars, planets, and life? The landscape offers a radical answer. We're not special, we're simply one outcome in an endless cosmic lottery. Most universes in this vast ensemble would be sterile, with physics too chaotic or too inert to sustain complexity. But statistically, a tiny fraction would hit the jackpot, landing on the precise combination of parameters that permit galaxies to form, atoms to bond, and consciousness to emerge. This statistical inevitability is the anthropic principle in action, a selection effect explaining why we find ourselves in a universe that seems improbably hospitable. Picture walking through a library where every book contains a complete, self-consistent set of physical laws. Most are gibberish, unreadable, nonsensical scribbles. But by sheer chance, a handful tell coherent stories, and we're characters in one of those rare volumes. The twist: the library isn't hypothetical. According to theorists like Leonard Susskind, the landscape isn't just a metaphor, it's a mathematical reality emerging from string theory's equations. The way Calabi-Yau manifolds curl their extra dimensions determines the behavior of strings, which in turn fixes the universe's constants. Change the manifold's shape slightly, and you'd rewrite the laws of physics overnight. Critics argue that the landscape turns science into a cosmic game of chance, where anything can be explained away by invoking an infinitely varied multiverse. But supporters counter that it's the logical extension of quantum mechanics and inflation, a framework where every possible outcome must occur somewhere. The landscape also offers testable predictions. If our universe is one bubble among many, collisions with neighboring bubbles could leave imprints in the cosmic microwave background, faint bruises from a long-ago encounter with another reality. Telescopes like Planck have searched for these anomalies, though definitive evidence remains elusive. The philosophical implications are dizzying. If the landscape is real, then the universe isn't just stranger than we imagine. It's stranger than we can imagine, a cosmic kaleidoscope where every twist reveals new laws, new dimensions, new possibilities. Somewhere out there, a version of reality might have 4 spatial dimensions, allowing for knots that can't be untied and geometries beyond comprehension. Another might have dark matter particles so massive they collapse into black holes instantly. The landscape isn't just a theory, it's an invitation to rethink our place in the grandest possible scheme, where even the most fundamental truths might be local bylaws in an infinite cosmic metropolis. And if that's the case, then the search for a theory of everything isn't about finding the universe's rule book, it's about discovering which page we're on. Ever wondered why gravity feels so weak compared to other forces? The answer might lie in the warped geometry of hidden dimensions like cosmic hills and valleys bending the very fabric of reality. In the late 1990s, physicists Lisa Randall and Raman Sundram proposed a revolutionary twist on extra dimensions. Instead of imagining them as tiny, curled-up loops, they suggested these dimensions could be vast but warped, like a stretched rubber sheet sagging under an invisible weight. Picture standing on a steep hillside. The slope beneath your feet feels solid, but the valley below seems distant, almost unreachable. That's how gravity might behave in their model, concentrated near our brain but diluted as it leaks into the warped depths of higher dimensional space. Unlike the Kaluza-Klein idea of compactified dimensions, the Randall-Sundram model imagines one extra dimension, an expansive 5th dimension where gravity's strength fades exponentially as you move away from our brain. Think of it like a radio signal weakening as you drive farther from the tower. Electromagnetism and nuclear forces, however, remain anchored to our brain like lights strung along a tightrope. This creates a striking imbalance. Gravity spreads thin into the bulk, making it appear feeble here, while other forces stay local and strong. The mathematics behind this is surprisingly elegant. The warping is governed by an exponential function, a cosmic filter that dampens gravity's influence without altering other interactions. It's as if our universe sits at the crest of a dimensional wave, where gravity's pull slips downhill into the unseen. This model didn't just solve the hierarchy problem, it turned it on its head. Instead of asking why gravity is so weak, Randall and Sundram showed it might not be weak at all. From the perspective of higher dimensions, gravity could be as powerful as the other forces, but its effects are muffled by the warped geometry of space-time. Imagine shouting into a pillow. Your voice hasn't gotten quieter, but the sound is absorbed by the fabric. Similarly, gravity's true strength might be smothered by the folds of an extra dimension we can't perceive. Experimental tests remain elusive but tantalizing. If gravity leaks into a warped 5th dimension, particle colliders might produce microscopic black holes or exotic high-energy gravitons, ghostly particles that carry gravitational force. The Large Hadron Collider has hunted for these signatures, though none have yet emerged. Yet the theory's elegance keeps it alive. It doesn't require finely tuned parameters or undiscovered particles. just a subtle reshaping of spacetime's hidden architecture. Beyond the math, this idea reshapes how we see the cosmos. Our universe might not float in empty void but cling to the edge of a dimensional rift, with gravity's whispers echoing from depths we'll never see. And if Randall and Sundram are right, then every falling apple, every orbiting planet, is a testament to the unseen contours of reality, a reminder that even the most familiar forces are strangers in a far stranger land. What if the universe is built like an endless set of Russian nesting dolls where patterns repeat themselves on every scale, from the quantum realm to the vast cosmic web? This is the mesmerizing premise of the fractal universe hypothesis, a theory suggesting reality isn't just structured in hidden dimensions, but operates along fractional, in-between scales that defy traditional geometry. At first glance, the idea seems borrowed from a surrealist painting, but its roots dig deep into rigorous mathematics, thanks to pioneers like Benoit Mandelbrot, who revealed how nature brims with self-similar patterns. Coastlines, fern leaves, even the branching of blood vessels all share this quality. Zoom in or out, and you'll find echoes of the same shapes. Now imagine applying that principle to the cosmos itself, where galaxy clusters mirror the distribution of atoms and black holes resemble swirling vortices in a stream. The math behind this hinges on fractal dimensions, numbers that aren't whole integers like 1, 2, or 3, but fractions in between. A crumpled piece of paper, for instance, isn't a smooth two-dimensional sheet, nor a solid three-dimensional object. It's something closer to 2.5 dimensions, its surface infinitely complex under magnification. Apply this to space-time, and suddenly the universe's architecture takes on a new texture. Cosmic voids and filamentary structures in the large-scale distribution of galaxies aren't random. They might follow fractal scaling laws, hinting at a deeper, dimensional intricacy woven into the fabric of reality. Even anomalies in the cosmic microwave background, the afterglow of the Big Bang, show fluctuations that some researchers argue align suspiciously well with fractal predictions, like cosmic fingerprints smudged across the sky. Critics counter that a truly fractal universe would conflict with the cosmological principle, the bedrock assumption that matter is evenly distributed at the largest scales. Yet intriguingly, galaxy surveys keep revealing unexpected clumping structures so vast they shouldn't exist under standard models, like the Hercules Corona Borealis Great Wall, a galactic filament stretching over 10 billion light-years. Could these be glimpses of a fractal cosmos? If so, it would mean our universe isn't just expanding, it's unfolding, layer by layer, in a dance of infinite complexity. The philosophical implications are profound. A fractal universe suggests there's no fundamental scale, no bottom or top to reality, only an endless recursion of patterns. Black holes might birth new universes in their cores, each echoing the parent cosmos like a Mandelbrot set's infinite iterations. Even time could behave fractally, with events repeating across epochs like ripples in a pond. Whether this hypothesis holds or not, it challenges us to see the cosmos not as a static stage, but as a living tapestry where every thread, no matter how small, contains the blueprint of the whole. And if that's true, then the key to understanding existence might lie not in searching for hidden dimensions, but in learning to read the universe's endless, repeating rhyme. What if the universe didn't begin with a bang, but with a whisper? That's the hauntingly beautiful premise of Roger Penrose's conformal cyclic cosmology, a theory so radical it suggests our cosmos isn't the first and won't be the last, but instead one link in an endless chain of universes, each dying only to be reborn in a cycle stretching to eternity. At the heart of this idea lies a simple but profound observation. As the universe expands toward heat death, all matter and structure will eventually dissolve into featureless radiation, a state eerily similar to the smooth, uniform conditions of the Big Bang. Penrose saw this symmetry not as coincidence but as a clue. The end of one universe, he proposed, could be the silent seed of the next, with infinity itself bridging the gap through the hidden geometry of higher dimensional phase space. The mechanics hinge on something called conformal rescaling, a mathematical transformation that lets you zoom in or out on spacetime without losing its essential shape. Picture an endlessly repeating fractal where each iteration looks identical no matter how far you zoom. Penrose's twist was to apply this to the entire universe. As one epoch fades into radiation, its vast, cold emptiness can be rescaled to match the hot, dense singularity of a new Big Bang, all within a higher dimensional framework where time and scale become fluid. It's as if the universe hits a cosmic reset button, not by collapsing back to a point, but by redefining what a point even means. The most tantalizing evidence for this wild idea comes from an unexpected place, the cosmic microwave background. Penrose and his collaborators claim to have found faint, concentric rings in the afterglow of the Big Bang patterns they call Hawking points, named after Stephen Hawking. These rings, they argue, are the gravitational echoes of supermassive black holes from a previous universe, their radiation imprinted like ghostly fingerprints on the newborn cosmos. Think of throwing a stone into a pond, then watching the ripples freeze solid only for those frozen waves to become the starting point for a new pond, carrying traces of the old one forward. Critics have pushed back, questioning whether these patterns are statistical flukes or artifacts of data analysis. But if Penrose is right, the implications rewrite not just cosmology, but the nature of reality itself. There's no true beginning or end, only transformation, an infinite dance of creation where each universe inherits subtle scars from its ancestors. Black holes, often seen as cosmic dead ends, become the scribes of eternity, encoding information across eons in ways we're only beginning to decipher. The theory's elegance lies in its economy. It doesn't invent new physics so much as repurpose old ones, showing how the universe's death throes could, through the lens of higher dimensional geometry, become its rebirth. And if conformal cyclic cosmology holds, then our universe isn't a one-time marvel. It's a single note in an endless symphony, with each crescendo of annihilation giving rise to the next movement, echoing across dimensions we've yet to name. Could consciousness itself be a bridge to dimensions beyond our perception? Some of the boldest theories in neuroscience and mysticism suggest that the human mind isn't just a product of the brain. It's a multidimensional phenomenon tapping into realms science has yet to map. Take Carl Pribram's holographic brain model, which proposes that memories aren't stored in specific neurons, but are instead scattered across the brain like interference patterns on a hologram. Just as a single fragment of a holographic plate can reconstruct an entire image, Pribram argued that every part of the brain might contain the whole of our experience. But here's the twist: holograms rely on the interference of waves in three-dimensional space, while the brain's holographic properties could hint at processing in higher dimensions, where information is encoded in ways our classical physics can't yet explain. This idea dovetails eerily with accounts from meditators and mystics who describe states of consciousness that defy conventional spatial logic. The so-called astral planes of esoteric tradition, for example, are often depicted as layered realities where time and space behave fluidly, a description suspiciously reminiscent of modern physics' curled-up dimensions. In these states, practitioners report traversing vast distances instantaneously or perceiving objects from multiple angles at once, as if their awareness had slipped into a geometry beyond our own. Even near-death experiences, with their recurring motifs of tunnel vision and life reviews, could be interpreted as the mind brushing against a higher dimensional topology, where past, present, and future coexist like pages in a book. Skeptics dismiss such parallels as coincidence, but cutting-edge physics isn't so quick to dismiss the connection. Quantum mechanics already shows that particles can exist in superpositions multiple states at once until observed. Some theorists, like Stuart Hameroff, suggest this collapse might involve a proto-consciousness interfacing with hidden dimensions. In orchestrated objective reduction theory, quantum vibrations in microtubules, tiny structures inside neurons, could interact with spacetime's fundamental geometry, meaning our thoughts might literally ripple through the fabric of reality at scales we can't perceive. It's as if the brain isn't just a receiver of consciousness but a transducer, converting multidimensional data into the linear stream of awareness we experience. The implications are staggering. If consciousness operates in higher dimensions, then phenomena like telepathy or precognition might not be supernatural, just superdimensional. Imagine two people standing on opposite sides of a wall, unable to see or hear each other. From their two-dimensional perspective, communication seems impossible. But introduce a third dimension, and they could reach over the barrier effortlessly. Similarly, what we call psychic phenomena might simply be the mind navigating directions we haven't learned to measure. Even creativity could have a dimensional explanation. Moments of insight might arise when the brain momentarily accesses solutions from a higher dimensional library of possibilities. Of course, mainstream science remains wary, citing a lack of empirical evidence, yet the parallels persist. String theory's Calabi-Yau manifolds, with their intricate folds and vibrational modes, bear an uncanny resemblance to neural networks. The brain's 100 billion neurons, each with thousands of synapses, create a connectivity so vast it rivals the complexity of these hypothesized extra dimensions. Coincidence or clue, whether these theories ever gain traction, they challenge us to consider that consciousness might not be locked inside our skulls, but woven into the cosmos itself, a thread in a tapestry far larger than we've dared to imagine. And if that's true, then the greatest frontier of exploration isn't outer space, it's inner space, and the hidden dimensions that might lie within. What if the universe we experience isn't the base reality, but an elaborate simulation running on some unfathomable higher dimensional computer? This is the spine-tingling premise of the simulation argument, a theory that blurs the line between science and philosophy, suggesting our entire existence might be a carefully coded illusion. Philosopher Nick Bostrom laid the groundwork with his now famous trilemma. At least one of these statements must be true. Either nearly all civilizations self-destruct before reaching technological maturity, virtually no advanced civilizations care to run ancestor simulations, or we are almost certainly living in one. The unsettling part, many experts argue the first two options seem statistically unlikely, leaving the third as a very real possibility. Think of it like this. If even one advanced civilization in our cosmic history developed the ability to simulate conscious minds, whether for research, entertainment, or preservation, the number of simulated beings would quickly dwarf those in base reality. The math is chillingly simple. Imagine a future where humanity crafts hyper-realistic virtual worlds populated by sentient AI, now scale that up across billions of years and countless galaxies. The odds that we're the original, unsimulated minds shrink to near zero. Bostrom's trilemma isn't sci-fi, it's a statistical inevitability wrapped in existential dread. But how could a simulation account for hidden dimensions? Here's where digital physics enters the picture. Pioneers like Edward Fredkin and Konrad Zuse proposed that the universe might fundamentally operate like a cellular automaton, a vast, self-updating grid of information. In this view, what we perceive as three-dimensional space with mysterious extra dimensions could simply be data structures in a higher dimensional processor. The laws of physics would just be the algorithms governing how the simulation renders reality. Particles behaving weirdly in quantum experiments, that might be the program optimizing processing power, only calculating precise values when observed, like a video game engine loading textures as the player looks around. Even the holographic principle fits neatly here, with our three-dimensional universe projected from a two-dimensional boundary. just as a modern game engine constructs immersive worlds from flat code. The implications ripple outward in unsettling ways. Glitches in the matrix, déjà vu, quantum indeterminacy, or even UFO sightings could be bugs or artifacts of the simulation's architecture. The fact that we've hit hard limits in measuring reality, like Planck length and time, might not be fundamental barriers but system resolution caps. And if the simulation runs in higher dimensions, phenomena like entanglement become trivial. Particles only appear separate in our rendered three-dimensional space, while their data packets sit side by side in the processor's memory. The simulation hypothesis doesn't just explain hidden dimensions, it reimagines them as design features of a cosmos-sized virtual machine. Critics counter with Occam's razor: why posit an unfathomable simulation when the universe could just be as it appears? Yet the theory gains traction because it reframes persistent mysteries. Why does math describe nature so perfectly? Because math is the simulation's native language. How could life emerge in a seemingly fine-tuned universe? Because the parameters were deliberately set. Even consciousness, that hard problem of neuroscience, might be an emergent property of sufficiently complex code. Whether the simulation argument terrifies or exhilarates you, it forces a profound shift in perspective. If true, the search for hidden dimensions isn't just about uncovering the universe's secrets, it's about reverse engineering the very fabric of our programmed reality. And if we're living in some vast computational experiment, perhaps the greatest discovery wouldn't be finding extra dimensions, but realizing we're standing on the other side of the screen. Richard Feynman once described quantum mechanics like this: if you want to know how a particle gets from point A to point B, don't imagine it taking one path, imagine it taking every possible path simultaneously. This radical idea, formalized as the path integral formulation, suggests particles don't just move through space, they sample every conceivable route, zigzagging through time and distance in a probabilistic haze before choosing where to land. But here's where it gets stranger. What if some of those paths aren't just winding through our familiar three dimensions? What if quantum particles are secretly slipping into hidden dimensions, breaching geometric barriers we can't see, to explain the bizarre phenomenon of superposition? Picture a drop of ink diffusing through water. From afar, it spreads smoothly in all directions, but zoom in, and you'd see individual ink particles jittering along chaotic, unpredictable trajectories. Feynman's insight was that quantum particles behave similarly, except their jittering isn't random, it's a computation. Every possible path, no matter how improbable, contributes to the particle's final position, with some paths weighted more heavily than others. Now imagine some of those paths don't just meander through length, width, and height, they tunnel through extra-spatial dimensions like shortcuts through the bulk of reality. A particle appearing to vanish and reappear in our three-dimensional world might simply have dipped into a fourth spatial dimension, taken a detour, and re-emerged elsewhere. It's as if the particle's superposition isn't just a blur, it's a multidimensional itinerary. This idea gains traction when you consider how path integrals handle infinity. Traditional quantum mechanics runs into headaches with particles behaving as both waves and points, leading to mathematical singularities. But in higher dimensional frameworks, those infinities can smooth out, like fitting a jagged puzzle piece into a larger, softer space. String theorists like Edward Witten have shown how Calabi-Yau manifolds could act as geometric filters, selecting which paths contribute meaningfully to a particle's behavior while cancelling out the nonsensical ones. In this view, superposition isn't just a particle being everywhere at once. It's the particle existing in a higher dimensional landscape where everywhere includes directions we can't point to. The implications ripple beyond theory. If particles sample extra-dimensional paths, it could explain why quantum objects seem to know about obstacles they haven't yet encountered, like electrons weaving through double-slit experiments as if rehearsing every possible outcome. Perhaps they're not magic, just navigating a richer spatial playground. Even the famous uncertainty principle might reflect our limited perspective. When we pin down a particle's position, its momentum becomes uncertain not because nature is fuzzy, but because we're ignoring its higher dimensional excursions. Critics argue this is speculative without direct evidence. Extra-dimensional paths remain elegant math, not proven physics, yet the math itself is compelling. Path integrals already unify quantum mechanics with statistical physics, and adding dimensions could bridge the gap to gravity. If gravity is weak because it leaks into higher dimensions, as some theories suggest, then particles might be slipping through those same folds whenever they enter superposition. The double-slit experiment's infamous which-way paradox, where observing a particle's path collapses its wave function, could be a dimensional red herring. Our act of observation might anchor the particle to our brain, cutting off its multidimensional routes. Whether hidden dimensions sculpt quantum behavior or not, Feynman's framework reshapes how we see reality. The universe isn't just strange, it might be bigger than we thought, with particles threading paths through geometries we can't perceive. And if that's true, then every quantum mystery, from entanglement to tunneling, could be a postcard from a dimension we've yet to visit. What if space-time isn't the foundation of reality, just a shadow cast by something far more elegant? That's the radical proposition of twistor theory, Roger Penrose's daring attempt to rewrite physics, not by adding hidden dimensions, but by dissolving space-time itself into a realm of pure geometry. Forget the four familiar dimensions of length, width, height, and time. Twistors replace them with a dazzling new framework where complex numbers, those strange mathematical hybrids of real and imaginary quantities, weave together light, gravity, and quantum mechanics into a single, luminous tapestry. At its core, twistor theory flips the script on how we describe the universe. Instead of starting with points in space-time, it begins with twistors, abstract objects that represent not just where and when something happens, but how light itself propagates through the void. Picture a beam of sunlight streaming through a prism. In traditional physics, you describe its path using coordinates, positions in space, and moments in time. But twistors capture something deeper, the intrinsic relationship between that light ray's energy, its polarization, and its direction of travel, all encoded in complex number geometry. It's as if space-time is just the clumsy projection of a richer, more symmetrical reality, like trying to describe a symphony by only reading the sheet music for one instrument. The magic lies in how twistors handle quantum weirdness. In standard quantum field theory, particles interact at specific points, leading to mathematical infinities that require clunky fixes. Twistor space smooths these rough edges by treating particles as extended objects in a complex number landscape, where interactions become geometric dances rather than chaotic collisions. Imagine two fireflies tracing glowing arcs in the dark. From our limited perspective, they might seem to abruptly change direction when they meet, but in twistor space, their paths form graceful curves, intersecting in ways that reveal deeper patterns. This elegance isn't just aesthetic, it's practical. Twistor-inspired methods have already revolutionized calculations in particle physics, turning pages of grueling algebra into sleek geometric intuition. Yet the theory's boldest claim lies in its approach to quantum gravity. By framing spacetime as emergent rather than fundamental, twistors offer a fresh path around the contradictions that plague string theory and loop quantum gravity. In this view, the fabric of reality might arise from entangled twistor networks, with gravity emerging from their collective geometry, like the surface tension of a pond arising from countless water molecules. Even black holes, those spacetime warping enigmas, take on new meaning. Their event horizons could be shadows of twisted twistor configurations, their singularities smoothed into knots of complex geometry. Of course, challenges remain. Twistor theory has yet to fully incorporate massive particles like electrons, and its mathematical beauty hasn't yet yielded testable predictions to rival inflation or supersymmetry. But its influence grows quietly, like a subterranean river reshaping the landscape above. From the discovery of amplituhedrons, geometric objects that simplify particle interactions, to new insights about the holographic principle, twistor mathematics keeps revealing hidden connections. Penrose's vision dares us to reconsider not just how the universe works, but what it fundamentally is. If twistors are real, then spacetime is a crude approximation, a grainy snapshot of a reality too luminous, too interconnected for our classical intuition to grasp. And somewhere in that complex number symphony, the answers to quantum gravity might already be written, waiting for us to learn the language. Imagine the universe not as a smooth fabric, but as a seething ocean of microscopic geometric fragments, each a fleeting spark of dimension, flickering in and out of existence. This is the startling vision of causal dynamical triangulations, a theory that dares to rebuild spacetime from the ground up using nothing but tiny, interconnected simplices, the mathematical term for triangular building blocks in higher dimensions. Think of it like cosmic Lego. Instead of assuming spacetime is fundamental, the theory suggests it's an emergent property, stitched together from countless quantum interactions between these elementary shapes. At its core, the approach is disarmingly simple. Picture spacetime fractured into four-dimensional chunks, tetrahedrons, in a hypertriangulated lattice. Each chunk adheres to strict causal rules. They must connect in ways that preserve the flow of time, preventing paradoxes where effects precede causes. Run a computer simulation of these interactions over astronomical iterations, and something remarkable happens. The chaotic jumble of triangles begins to self-organize, smoothing out into the familiar four-dimensional continuum we recognize as spacetime. It's as if the universe is performing origami at the quantum scale, folding randomness into order through sheer statistical inevitability. What makes this radical is how it sidesteps the infinities plaguing other quantum gravity theories. In general relativity, singularities lurk inside black holes where curvature becomes infinite. But in the triangulated universe, there's no such thing as infinite density, just a dynamical network of finite geometric pieces, each contributing to the whole. Even the Big Bang transforms from a mysterious singularity into a phase transition, like ice melting into water, where the underlying quantum geometry rearranges itself into classical spacetime. The theory's predictions are eerily precise. At extremely small scales around the Planck length, spacetime resembles a frothing fractal foam, with triangles popping in and out of existence. But zoom out, and this quantum turbulence averages into the smooth cosmic stage Einstein described. Intriguingly, this foam-like structure might leave detectable imprints. Some models suggest high-energy gamma rays could travel slightly slower than light if they're buffeted by microscopic spacetime fluctuations, a potential signature astronomers are actively hunting. Yet the true brilliance lies in how causal dynamical triangulations embrace imperfection. Unlike string theory's pristine extra dimensions or loop quantum gravity's elegant spins, this framework thrives on disorder. It's a theory of emergence where complexity arises not from top-down design, but from bottom-up chaos, a cosmic lesson in how simplicity begets grandeur. Whether it's the final answer or just a stepping stone, one thing is clear. The universe's blueprint might be written in a language of shapes we're only beginning to decode. The Higgs field, often called the universe's molasses, is what gives particles their mass, slowing some down while letting others zip through untouched. But what if this cosmic slowdown isn't just a property of particles themselves, but a side effect of hidden dimensions tugging at them from beyond our perception? Picture a marble rolling across a flat table. On its own, it glides smoothly. Now tilt the table slightly, the marble slows as if something invisible is weighing it down. That's the Higgs effect in a nutshell. but instead of a tilted table, imagine the marble's path dipping into an unseen fourth spatial dimension, where extra geometry creates resistance we interpret as mass in our three-dimensional world. This idea isn't pure speculation. Certain higher dimensional theories, like those inspired by string theory's brane world scenarios, suggest the Higgs boson, the particle associated with the field, might actually be a vibration spilling over from compactified dimensions. In these models, what we call mass could be the fingerprint of particles interacting with the curled-up geometry of Calabi-Yau manifolds or warped branes. Think of it like a sailboat moving through water. From above, you only see the boat's speed, but beneath the surface, drag from hidden currents determines how fast it can go. Similarly, particles gaining mass might be feeling the drag of higher dimensional geometry. The math behind this is as elegant as it is mind-bending. In some extra-dimensional frameworks, the Higgs field emerges not as a fundamental force, but as a kind of structural echo, a geometric artifact of how particles move through folded dimensions. Just as a guitar string's pitch depends on its length and tension, the Higgs mechanism could arise from the way particles vibrate through multidimensional space. Some versions of this theory even suggest that the Higgs boson behaves like a messenger particle, shuttling between our observable brane and hidden dimensions, its properties shaped by the geometry it traverses. Why does this matter? Because if the Higgs mechanism is rooted in extra dimensions, it could solve one of physics' biggest head-scratchers, the hierarchy problem. The Higgs boson's measured mass is suspiciously light, about 125 times heavier than a proton, yet trillions of times lighter than the Planck scale where quantum gravity dominates. This absurd fine-tuning seems unnatural unless something is suppressing its mass behind the scenes. Warped extra dimensions could provide that very suppression, with gravity's leakage into the bulk naturally offsetting the Higgs's weight. It's like a seesaw balanced by unseen hands, the higher dimensions acting as a counterweight to keep mass stable in our universe. Experiments at the Large Hadron Collider have yet to find direct evidence linking the Higgs to extra dimensions, but subtle anomalies persist. The Higgs sometimes decays in ways that don't quite match the Standard Model's predictions, as if unseen factors are tweaking its behavior. Future particle colliders or precision measurements of cosmic inflation might spot the fingerprints of these dimensional currents, tiny deviations that reveal the Higgs isn't just a field, but a bridge to realms beyond our own. At its heart, this theory reshapes how we see mass itself. Rather than an intrinsic property, mass could be a cosmic mirage, an illusion born from particles navigating hidden folds in reality's fabric. And if that's true, then every atom in your body, every star in the sky, owes its existence not just to the Higgs, but to the secret geometry of dimensions we've yet to map. Einstein's equations once suggested a serene, if bizarre, reality. Black holes might be cosmic backdoors, their crushing gravity bending spacetime so severely that the singularity connects to another point in the universe, or another universe entirely, via an Einstein-Rosen bridge, better known as a wormhole. But when quantum mechanics enters the picture, this elegant geometry erupts into chaos. Enter the firewall paradox, an inferno of quantum fury blazing at the black hole's event horizon, threatening to burn any traveler alive the moment they cross the threshold. How did we go from serene bridges to raging firewalls? The answer might lie in the strange marriage of two seemingly unrelated ideas, entanglement and extra dimensions. The trouble starts with information. Quantum mechanics insists it can never be destroyed, yet black holes seem to erase it as they evaporate via Hawking radiation. To solve this, theorists propose that entangled particles near the event horizon encode the disappearing information, but this creates another crisis. If entanglement stitches spacetime together, as the audacious ER=EPR conjecture suggests, then every pair of entangled particles might be connected by microscopic wormholes threading through higher dimensions. Picture two sheets of paper crinkled close together from our three-dimensional view. They're separate, but a hidden fourth dimension could allow threads to pass between them unseen. Black holes entangled with each other wouldn't just share quantum links. Their event horizons might literally fuse in the bulk of higher dimensional space, forming a wormhole that bypasses the singularity entirely. This reshapes the firewall debate dramatically. If an infalling astronaut doesn't plunge toward a singularity but instead enters a wormhole woven from entanglement, the horrific firewall might dissolve into an illusion, a mirage caused by our limited perspective. From outside the black hole, quantum corrections could make the horizon appear ablaze, while from within, the traveler glides smoothly into another region of spacetime. It's like watching a movie where a character steps into a painting. To the audience, they vanish into flat pigment, but in the story's hidden dimensions, they've simply walked into a larger world. Yet skeptics argue this solution trades one paradox for another. If wormholes rescue information, they might also allow time travel or violate quantum no-cloning theorems. Others counter that higher dimensions could enforce cosmic censorship, their geometry preventing contradictions like a careful editor redacting paradoxes from reality's script. The truth remains elusive, but the stakes couldn't be higher. If ER equals EPR holds, then spacetime isn't just curved, it's stitched together by quantum threads humming through dimensions we can't see, and black holes aren't tombs but translators, rewriting the laws of physics in a language woven from entanglement and extra-dimensional geometry. Perhaps the most poetic twist is this: the same higher dimensions that birth firewalls might also extinguish them, their hidden folds offering escape routes from the very crises they create. Whether firewalls rage or fade, one thing is clear: the universe's most violent enigmas might be solved not by looking deeper, but by realizing we've been missing entire directions. The universe seems suspiciously hospitable to life, almost as if it were designed that way. The precise strength of gravity, the exact mass of the electron, even the delicate balance of dark energy enabling galaxies to form. Tweak any of these values slightly, and stars, planets, and life itself would be impossible. This eerie perfection is known as the fine-tuning problem, and it's one of cosmology's deepest enigmas. How can the fundamental constants be so exquisitely calibrated for existence? The anthropic multiverse offers a daring solution. What if there isn't just one universe, but an unfathomable array of them, each with different physical laws, different dimensions, and only a rare few capable of hosting conscious observers like us? At its core, this idea hinges on probability. In an infinite higher dimensional landscape of universes, some with 4 spatial dimensions, others with 7, some where gravity crushes atoms instantly, others where matter never clumps into stars, statistically, a handful will inevitably land on the right parameters for life. We find ourselves in one of those lucky universes not because it's special, but because we couldn't exist anywhere else. Think of it like a cosmic lottery. If you buy a single ticket, winning seems miraculous, but if trillions of tickets are sold across countless parallel draws, someone has to hit the jackpot. The anthropic principle flips the fine-tuning question on its head. Instead of asking why our universe is perfect, it suggests perfection is inevitable because only in such a universe could anyone be around to ask the question. The connection to hidden dimensions here is profound. String theory's landscape of possible vacuum states, each a unique configuration of curled-up Calabi-Yau manifolds, provides the raw material for this multiverse. Some versions of the theory suggest these extra dimensions don't just influence particle physics, they might determine whether a universe permits complexity at all. A 6-dimensional universe, for example, could have gravity so strong that matter collapses into black holes before life arises. A 2-dimensional one might lack the geometric richness for complex chemistry. Our 3 spatial dimensions could be a Goldilocks zone, not too many, not too few, where the laws of physics align just right for observers to emerge. Critics argue this explanation feels like a cheat, a way to sidestep the search for deeper mechanisms. But proponents counter that the anthropic multiverse isn't just speculative philosophy, it's testable science. If our universe is one bubble in a frothing multiverse, collisions with neighboring bubbles could leave scars in the cosmic microwave background, subtle temperature variations or circular patterns signaling a long-ago brush with another reality. Future telescopes scanning the sky for these anomalies might find hard evidence that we're not alone in the metacosmos. Even more intriguingly, if higher dimensions shape the constants of nature, then variations in those constants across space, like slight shifts in the fine structure constant, could hint at regions where different dimensional geometries dominate. The philosophical stakes are dizzying. If the anthropic multiverse is real, then the very act of observation becomes a cosmic filter. Dimensions aren't fixed, they're variables in a vast equation, with conscious beings like us acting as living proofs of certain solutions. Our existence isn't an accident, it's a statistical inevitability, written into the geometry of higher dimensional space. And somewhere out there, in the infinite bulk of reality, other versions of us might be marveling at their own improbable luck, unaware that their universe is just one thread in a tapestry too vast to comprehend. The true miracle isn't that we're here, it's that the cosmos conspired to make asking the question possible at all. Dark energy, the mysterious force accelerating the universe's expansion, has long been a puzzle wrapped in an enigma. We know it makes up nearly 70% of the cosmos, yet its true nature remains shadowed in uncertainty. The standard explanation, Einstein's cosmological constant, treats dark energy as a static property of space itself, a kind of background hum woven into the vacuum. But what if that hum isn't constant at all? What if it's the fading echo of something far stranger, the slow unraveling of hidden dimensions? This idea flips the script on dark energy by linking it directly to the geometry of extra dimensions. Imagine a room filled with tightly coiled springs, each one vibrating at a different frequency. Over time, those springs lose tension, their energy dissipating as heat. Now replace the springs with compactified dimensions, tiny, curled-up spaces predicted by string theory, and you've got the core of this radical proposal. As these dimensions decay or relax over cosmic time, their energy doesn't vanish. It leaks into our observable universe as a gentle but persistent pressure driving galaxies apart. It's as if the fabric of reality itself is exhaling, its breath pushing the cosmos toward endless expansion. The numbers behind this are startlingly elegant. In some models, the rate of dimensional decay matches the observed strength of dark energy almost exactly. Unlike the cosmological constant, which remains stubbornly unchanging, this dynamic dark energy evolves, starting strong in the early universe and tapering off as extra dimensions stabilize. This could explain why dark energy only recently became dominant, around 5 billion years ago, after gravity had its chance to sculpt galaxies and clusters. It's a cosmic coincidence no longer. The timing aligns because the decay process itself has a lifespan, like a battery slowly draining. But how would decaying dimensions leave fingerprints? One clue might lie in the equation of state, a measure of how dark energy's density changes over time. The cosmological constant predicts a fixed value of -1, but if dark energy stems from relaxing dimensions, that number could drift slightly, leaving subtle imprints in the large-scale structure of the universe. Future telescopes like Euclid or the Vera Rubin Observatory could spot these deviations, hunting for telltale wrinkles in the distribution of galaxies or anomalies in the cosmic microwave background. Even more intriguingly, if compactified dimensions are unraveling, their demise might produce ultra-low frequency gravitational waves, ripples in spacetime so faint they'd require detectors thousands of times more sensitive than LIGO to catch. Critics rightly ask why we'd invoke extra dimensions when the cosmological constant, for all its mysteries, fits the data reasonably well. The answer lies in unification. Dark energy as dimensional decay doesn't just explain cosmic acceleration. It ties into string theory's broader vision, where the shape and stability of hidden dimensions govern everything from particle masses to the strength of forces. In this framework, the universe's fate isn't written in static equations but in the dynamic geometry of higher dimensional space. A cosmos where dark energy fades could eventually see expansion slow or even reverse, a dramatic contrast to the bleak, infinite emptiness predicted by the cosmological constant. The philosophical implications are profound. If dark energy is dimensional decay, then the universe isn't just expanding, it's transforming, its very architecture shifting beneath our feet. Dimensions we'll never see could be the silent architects of our cosmic destiny, their quiet unraveling scripting the fate of galaxies. And somewhere in that process, the answers to physics' greatest riddles might lie curled up, waiting to be unfurled. Numbers rule the universe, but not just the ordinary ones we count with. Hidden beneath the equations of particle physics might lie a bizarre 8-dimensional number system called the octonions, a mathematical realm so strange it could rewrite our understanding of reality itself. Unlike the familiar real numbers or even complex numbers, octonions refuse to play by the usual rules. Their multiplication isn't associative, meaning the order in which you multiply them changes the result. It's as if 2 times 3 sometimes equaled 5 and other times 7, depending on how you ask the question. Yet this very strangeness might be the key to unifying the forces of nature, with our 3-dimensional world merely a shadow cast by these richer, more intricate structures. The story begins with a curious pattern in physics. The fundamental forces and particles seem to align eerily well with certain symmetries found in octonions. Take the Standard Model, our best map of particle behavior. Its symmetries, the invisible geometries governing how particles interact, match uncannily with mathematical properties of octonions. For instance, the 8 gluons that mediate the strong nuclear force mirror the 8 dimensions of octonionic space. Even quarks, the building blocks of protons and neutrons, arrange themselves in ways that hint at an underlying octonionic logic. It's like discovering all the words in a language secretly follow the rhythm of a song no one's ever heard. Why would nature care about such exotic math? One compelling answer lies in the exceptional nature of octonions. Among all possible number systems, they occupy a rarefied place called the exceptional Jordan algebra, a structure so unique it appears tailored for physics. When theorists like Cole-Fury and others explored this connection, they found octonions could naturally generate the Standard Model symmetries, almost as if particles were vibrations not in space-time, but in an 8-dimensional numerical landscape. Picture a piano where each key represents a dimension. The notes we perceive as particles might just be chords played across octonionic keys, their harmonies shaping the laws of reality. But here's the twist. Octonions don't just unify, they also explain why our universe seems clipped down to 3 spatial dimensions. In certain octonionic models, interactions that look messy or random in our familiar 3D world resolve into elegant simplicity when viewed through 8-dimensional lenses. Imagine trying to describe a shadow puppet's motion without knowing about the hand casting it. The movements seem arbitrary. But once you see the full dimensional source, everything clicks. Similarly, quantum quirks like particle spin or charge quantization might emerge from higher dimensional octonionic geometry, with our universe acting as a lower dimensional projection of deeper mathematical truths. Critics argue that octonion-based theories remain speculative, lacking experimental verification. Yet their mathematical allure keeps drawing physicists deeper into the maze. Unlike string theories, Calabi-Yau manifolds, or loop quantum gravity spin networks, octonionic models don't require inventing new physical entities, just recognizing that numbers themselves might hold the blueprint of existence. Future particle colliders or precision tests of quantum symmetries could tilt the scales, searching for octonionic fingerprints in the dance of particles. Whether octonions ultimately underpin reality or not, their exploration reveals something profound. The universe might not just be described by math, it could be math, a living symphony of abstract relationships playing out in dimensions beyond our perception. And if that's true, then every proton, every photon is a note in a song we're only beginning to decipher, resonating through a cosmic scale we've yet to fully hear. Imagine 1,000 possible versions of reality flickering in and out of existence, a quantum soup where every outcome coexists until, suddenly, one version solidifies into the world we experience. Quantum Darwinism proposes that this transition from quantum weirdness to classical certainty isn't random. It's a process of natural selection playing out in the vast, abstract landscape of Hilbert space, a higher dimensional mathematical realm where quantum states live. But here's the twist. What if the dimensions of Hilbert space aren't just abstract tools? What if they're the hidden scaffolding that shapes reality itself, with our familiar three-dimensional world emerging as the fittest survivor in a constant battle for stability? At the heart of this idea is a profound shift in perspective. Traditional quantum mechanics treats observation as the moment a wave function collapses, like flipping a coin that only lands when you look. Quantum Darwinism flips the script. Observation isn't the cause of collapse, but the result of a deeper dynamic. As quantum systems interact with their environment, whether photons, air molecules, or even other particles, their states become redundantly imprinted across countless degrees of freedom. Only the most robust, durable states survive this process, while fragile superpositions decay away. Think of it like a game of telephone played across the universe, where the clearest, most consistent message gets amplified while the noise fades. Over time, the winners of this competition become the classical facts we take for granted: the position of a chair, the path of a planet, while the quantum possibilities remain hidden in Hilbert's unseen dimensions. Now, layer in the dimensional view. Hilbert space isn't confined to our familiar three dimensions. It's a sprawling, high-dimensional arena where quantum states evolve. Picture a vast, multi-layered chessboard where each square represents a possible configuration of reality, and every move branches into new dimensions of possibility. Quantum Darwinism suggests that classical reality emerges because certain states, those we ultimately perceive, are the ones most efficiently copied into the environment's Hilbert space. It's like a meme going viral. The states best adapted to replicate across higher dimensional interactions dominate, while the rest vanish into obscurity. This winnowing process could explain why we don't see quantum superpositions in everyday life, not because they don't exist, but because they're outcompeted by states better suited to survive dimensional entanglement. The implications ripple far beyond theory. If quantum Darwinism holds, it could bridge the gap between quantum mechanics and gravity, two frameworks famously at odds. In this view, spacetime itself might emerge from the same Darwinian process, with the geometry we perceive reflecting the most stable, reproducible patterns in Hilbert space. Even black holes, those cosmic information shredders, could be reinterpreted as environments where quantum states undergo extreme selection pressure, their event horizons acting like filters that only the fittest states traverse. Critics argue that this approach risks replacing one mystery with another. How does Hilbert space select preferred states? Yet the theory's elegance lies in its economy. It doesn't invent new physics but repurposes known principles of information and interaction. Future experiments probing quantum decoherence or the limits of classicality might reveal fingerprints of this hidden competition, showing how reality isn't handed to us, it's forged in the unseen dimensions of quantum evolution. Ultimately, quantum Darwinism doesn't just explain why we see a classical world, it redefines what reality is. The universe isn't a static stage, it's a dynamic, multi-dimensional arena where the laws we know are simply the reigning champions of an endless tournament. And somewhere in Hilbert's vast halls, every possible outcome still exists waiting for its chance to be copied, amplified, and maybe one day seen. Black holes aren't just cosmic vacuum cleaners, they're shredders tearing apart stars and seemingly erasing the information they consume. This violates one of quantum mechanics' most sacred laws, unitarity, the principle that information can never truly be lost. If a black hole swallows a book, the information inside shouldn't vanish, it should be encoded somehow, even if scrambled beyond recognition. But where, the terrifying answer might lie not inside the black hole, but in the hidden dimensions curled around it like an invisible safety net. Imagine tossing a handful of confetti into a fan. From one angle, the pieces seem to vanish into chaos. But if you could see from above, you'd realize they've simply scattered across a larger space, still traceable if you know how to look. Black holes might work the same way. As matter falls in, its information could get imprinted onto the event horizon's surface, a concept called the holographic principle, but the real twist is how. Higher dimensions could provide the extra room needed to preserve this data without violating quantum rules. String theory suggests that when a black hole evaporates via Hawking radiation, the information isn't destroyed. It's funneled through extra-dimensional channels like water draining through a hidden gutter. The radiation we detect might carry subtle fingerprints of that journey, encrypted in ways we're only beginning to decode. This isn't just abstract math. The AD/CFT correspondence, a framework linking higher dimensional gravity to quantum field theories, hints that black hole information could be stored in a dual reality, a lower dimensional shadow universe where every bit of lost data is perfectly preserved. Think of it like a cosmic rescue mission. When a particle falls into a black hole, its information doesn't plunge into oblivion, it's projected onto a higher dimensional buffer, like a backup saved to an unseen server. The event horizon becomes a kind of quantum printer, encoding data into the fabric of spacetime itself, with extra dimensions acting as the ink. Experiments might one day test this wild idea. If information escapes through higher dimensions, merging black holes could release gravitational waves with faint, telltale modulations, subtle wobbles in the signal that betray hidden structures. Even Hawking radiation itself, if ever detected directly, might carry anomalies that point to dimensional leakage. Until then, the paradox remains a tantalizing clue that the universe's most destructive phenomena might also be its most sophisticated archivists, with black holes not as tombs, but as librarians filing reality's secrets into shelves we can't yet see. Time crystals sound like something ripped from a science fantasy novel, structures that pulse and oscillate without ever losing energy, defying the universe's relentless slide toward entropy. But these aren't fictional. Nobel laureate Frank Wilczek first proposed them in 2012 as a new phase of matter, where atoms arrange themselves in patterns that repeat not just in space but in time. Imagine a snowflake that doesn't just sit there, it breathes, cycling through its shape once every second, then again forever without any energy input. It's as if these crystals have tapped into a hidden rhythm of reality itself. The secret might lie in dimensions beyond the ones we perceive. Most phases of matter, solids, liquids, gases exist in static equilibrium, their energy slowly dissipating as heat. Time crystals break this rule by existing in what's called temporal order, a state where their lowest energy configuration still involves perpetual motion. Wilczek's insight was that this could hint at an unseen temporal dimension, a direction in time beyond the linear flow we experience. Picture a record spinning on a turntable. From above, you see the needle tracing a perfect circle, but the groove itself is a spiral moving forward even as it cycles. Time crystals might be doing something similar, their oscillations riding the contours of a hidden temporal geometry. Experiments have since turned theory into reality. In 2017, researchers at Harvard and the University of Maryland created time crystals using chains of ytterbium atoms and nitrogen vacancies in diamond. These systems didn't just oscillate, they locked into beats that couldn't be explained by external forces alone, like pendulums swinging in perfect sync across a room without strings. Even more bizarrely, when disturbed, the crystals healed back to their rhythm, as if tethered to an invisible metronome. This resilience suggests their motion isn't just a fluke but rooted in something deeper, a symmetry of time itself, possibly unfurling in extra dimensions. String theory offers a tantalizing lens to view this. If space has hidden compactified dimensions, why not time? Some models propose that time crystals' oscillations are vibrations along a curled-up temporal dimension, too small to notice directly but whose echoes manifest as perpetual motion. It's like a guitar string vibrating at frequencies we can hear, while higher harmonics resonate in realms beyond our perception. These temporal dimensions wouldn't flow like our familiar time. They'd loop, creating closed paths where the end feeds back into the beginning, a cosmic ouroboros of cause and effect. Critics argue that time crystals don't truly violate thermodynamics, they redistribute energy rather than creating it. Yet their very existence challenges our understanding of equilibrium. If time crystals can harness hidden temporal dimensions, they might unlock technologies that seem impossible today. Quantum computers with error-resistant clocks, or engines that extract work from the fabric of time itself. More profoundly, they could be proof that time isn't a one-way river, but a multidimensional tapestry, and somewhere in its folds, the universe is still writing its own rhythm. What if the universe isn't just described by math? What if it is math? This is the mind-bending core of Max Tegmark's mathematical universe hypothesis, a theory so audacious it claims every logically consistent mathematical structure doesn't just model reality, it is reality. Imagine a cosmic library where every equation, every geometric form, every possible set of dimensions isn't an abstraction but a tangible existence. In this view, our universe, with its 3 spatial dimensions and quantum quirks, is just one shelf in an infinite archive, surrounded by realms where 12-dimensional geometries unfold. Time loops like Möbius strips, and gravity behaves like a kaleidoscope of ever-changing rules. Tegmark's framework strips away the distinction between map and territory. Normally, we think of math as a tool, a language we use to describe the universe's behavior. But the mathematical universe flips this. The reason math works so unnervingly well isn't because we're clever coders of nature's rules. It's because nature is those rules instantiated in physical form. Picture a fractal so detailed that every zoom reveals not just patterns, but entire worlds humming with their own physics. A 4-dimensional hypercube isn't just a thought experiment here. It's as real as the chair you're sitting on, existing somewhere in the ultimate ensemble of mathematical structures. This idea didn't emerge from pure philosophy. It's grounded in the eerie effectiveness of math in physics, from Einstein's equations predicting black holes decades before their discovery to quantum mechanics' uncanny precision. Tegmark argues this isn't coincidence, it's inevitability. If every mathematical structure exists objectively, then of course we find ourselves in one where math aligns perfectly with observation. But the wild corollary is that infinitely more structures exist where it doesn't. Realities with no observers, no stars, no recognizable laws, just pure alien logic playing out in dimensions beyond human comprehension. Critics push back, asking how such a theory could ever be tested. Tegmark offers subtle clues. If the mathematical universe is true, then certain features of our cosmos, like its low entropy at the Big Bang or the values of fundamental constants, might reflect deeper symmetries or computational simplicity in the mathematical source code. Future discoveries in quantum gravity or topology could reveal these fingerprints, showing our universe isn't just one random possibility, but a node in a vast, interlacing network of mathematical existence. The implications are humbling. It means Pythagoras's triangles and Turing's algorithms aren't inventions, they're discoveries, as real as mountains or galaxies, just waiting in the ensemble. It means a 12-dimensional universe where gravity repels and time shatters into branches isn't fiction, it's out there, humming in the cosmic background noise. And if Tegmark is right, then the ultimate truth isn't just stranger than we imagine, it's stranger than we can imagine, written in equations we've yet to learn how to read. From the intricate folds of Calabi-Yau manifolds to the holographic edges of our perceived reality, these theories stretch the imagination in ways even science fiction rarely dares, proposing that the cosmos might be vaster, stranger, and more interconnected than we've ever dreamed. Whether it's strings vibrating in unseen dimensions, brains colliding in a higher dimensional bulk, or the universe itself as a mathematical structure in an infinite ensemble, each idea offers a tantalizing key to unlocking physics' greatest mysteries: the weakness of gravity, the nature of dark matter, even the origins of space-time itself. Hidden dimensions aren't just wild speculation, they're a framework that could stitch together the fragmented pieces of modern physics. Think of them as the unseen stitches in reality's fabric, holding together quantum weirdness and cosmic-scale gravity in a single, elegant tapestry. Without them, black holes remain paradoxical, entanglement feels like magic, and the Big Bang's singularity defies explanation. But with extra dimensions in play, suddenly, the puzzle starts to make sense, like realizing a maze has secret passageways you never noticed. So which theory resonates with you? The cosmic ballet of string theory's 10 dimensions, the holographic universe's pixelated code, or perhaps the haunting possibility that we're living in a simulation running on some higher dimensional computer? There are no wrong answers, only frontiers of curiosity waiting to be explored. The beauty of these ideas isn't just in their answers, but in the questions they inspire. What does it mean for reality if time is a dimension we could theoretically traverse? How would our understanding of existence shift if dark matter is just matter we're dimensionally blind to? The journey doesn't end here. Every year, new experiments, from particle colliders to gravitational wave detectors, bring us closer to testing these extraordinary ideas. Maybe one day we'll peer beyond the veil and glimpse those hidden dimensions ourselves. Until then, the universe remains the ultimate mystery, inviting us to keep questioning, exploring, and marveling at its secrets. If you love diving into these cosmic riddles, don't forget to subscribe, because the next breakthrough might be just one theory away. And who knows, the key to it all could be lurking in dimensions we've yet to name.